Welcome back to episode 44 of the Quantum Science Seminar, which today will be about trapped ion quantum computing, but with molecular ions. As usual, we would like to have your questions. Please send us your questions to quantumscienceseminar@gmail.com or use the YouTube live chat at the right or at the bottom of your screen. You should also remember that there's a 30-second time delay between what we do here and what you see is live on YouTube. And with this, I'd like to hand over to Thomas, who will introduce our speaker today.
So good afternoon, everyone, and very welcome, hearty welcome to Dietrich Leibfried, who volunteered to give a presentation today. So a brief summary for those of you who don't know Didi yet, who is one of the landmark researchers in Eintrap physics. So Didi was born and raised a proper German and did his PhD with high honors at the LMU in Munich in 1995 with Ted Hensch, who is one of his actually many Nobel laureates who he was actually working with during his research. His work in Munich included work such as the absolute frequency measurement in hydrogen or measurements on the lamp shift in hydrogen and deuterium. He later on then, and actually a cool thing there, he was working with Ferdinand Schmidt-Kaller and other well-known professors already during that time, who is now in Mainz. He then completed his postdoc work at NIST in 1997, where he was working on the foundations for ion-trap quantum information processing, working with Dave Wineland on cooling of ions, and had colleagues such as Chris Monroe, who is now a professor in Maryland and Duke, or Roy Oseri, who is a professor at Weizmann Institute and one of the former speakers in the series. He came to Innsbruck. He was working with Rainer Blatt on the first experiments on quantum information processing, including realizing some of these really important features, such as addressing single ions in ion strings, implementing EID cooling together with Christian Roos, or cooling and coupling an ion to a high finesse cavity, which is now one of the foundations of building networks between remote ion trap quantum processors. In 2001, Didi returned to NIST and became their research associate, to then become a staff member in 2004, where he's now leading his own research group on quantum information processing with trapped ions. He became, in addition, a permanent lecturer at the University of Colorado in 2018. As you hopefully saw from this brief introduction, he has a very broad agenda of research, including quantum logic algorithms. He was working on scalable ion traps, implemented teleportation, error correction, Fourier transform, entanglement purification, many other things, but also included microwave control on trapped ions. And now, and all of that is complemented with a strong background on spectroscopy, cooling, and so on. And with that, we are very, very grateful for having Didi here to give this presentation now this afternoon.
All right. I hope everyone can hear me. Please let me know if you cannot hear me. And now you should be able to see my screen. Can you hear me? Is everything fine? All right, great. So first of all, of course, I want to thank Sebastian and the organizers of the Quantum Science Seminar for giving me a chance to speak here, and Tommy for the very, almost embarrassing introduction. What I want to talk about today is quantum logic control of a single molecular ion. And this talk would not be possible at all without the tireless work of James Jinwen Chow. It all started with some crazy ideas, and James really went to the lab and implemented all of this. And together with the team that you can see the names here, David Leibrand, Alejandra Coloppi, Dalton Chaffee, Christoph Kurtz, Yi-Heng Lin, Yu Liu, and Julian Schmidt, nothing what I would talk about today would be possible. To introduce the topic a little better, I can't resist to maybe show this somewhat stated quote from Erwin Schrödinger. We never experiment with just one electron or atom or a small molecule. And you've probably seen this a few times now. The reason why I still would like to bring it up here is that what we do here is we are not just experimenting with one atom or a small molecule. We are experimenting with one atom and a small molecule. So basically, we took Schrödinger's dream in the last let's say 70 years or so, and now we are even beyond what he never will experiment with. All this only became possible because Dave Wineland came up with a seminal idea in about 2002, which we call quantum logic spectroscopy. And quantum logic spectroscopy actually enables a lot of nice possibilities. Looking at molecules is only one of them. Dave had in mind that you could build optical clocks, for example, based on single aluminum ions, where the aluminum ion cannot be directly interrogated. And of course, there are many charged systems that cannot directly be interrogated, or it would be very hard, let's put it that way. For example, you can do this with highly charged ions. And there's great research, for example, at PTB with Schmidt and Jose Luis Crespo doing this, Pete Schmidt. And in our case, we look at the diatomic molecular ion. But what I want to stress even before starting is that we are looking at the rotation right now. We can probably extend this to the vibration, and diatomic molecules are not the only molecules that should be suitable for this. It should also be possible for polyatomic molecular ions. So hopefully this is just the beginning of a long story. And in principle, any charged system could be coupled to with these techniques. So it's a very universal techniques. You could think of electrons, antiprotons, and other charged systems, as long as they have optical transitions where you can drive sidebands, or maybe even microwave transitions with sidebands. So in other words, I think this technique that Dave introduced is basically the Swiss Army knife of ion trapping technology. And appropriately, as you can see, the Swiss Army knife producers have put a plus sign into their logo. So it's very appropriate for ions. If you don't take anything away from this talk, but this view graph, at least you've gotten the main message. And also, I hope this will guide you when things get a little hairy, maybe later on. The idea of quantum logic spectroscopy is that instead of using light, which was always the messenger for spectroscopy, you can also use motion as the messenger. And the idea is fairly simple. Suppose you have some charged object that has quantum transitions. You can drive this transition directly, and you would potentially not know that you've driven it. However, you can also drive it on a so-called sideband, where you add a little energy to the photon that drives this transition. And now you can basically make the state change and also put the particle from a state of rest to a state where it oscillates. Because it's electrostatically repulsing, has electrostatic repulsion with one of the ions we know and love here, when it starts moving, the ion that we know and love also starts moving. And this ion here, we can control very well. It's one of our standard ions. And now we can try to drive a transition here that has a photon with slightly not enough energy to make this transition. However, if you have the energy of the motion, we can basically make this transition. So without the motion, it doesn't work, but with the motion, it works. And then we can read it out. So it can either be a bright ion if the transition never happened, or it can be a dark ion if the transition happens. So basically, our quantum logic ion here gives us a message whether this transition here happened. Transition happens, motion, this ion is in motion, and finally, we get the message. So this is the basic idea in classical terms, of course, of quantum logic spectroscopy. And the first realization, as I already alluded to, was Pete Schmidt and Till Rosenband in 2005, when they used this to interrogate an aluminum ion that would have direct transitions in the vacuum, ultraviolet, which would be very hard to drive. All right, now the second hero of the talk here are molecules. And why are we interested in molecules? Basically, molecules can do more than atoms. In atoms, we have electronic transitions, and we also have, of course, fine structure and hyperfine structure, but that's about all we can say about atoms. With molecules, there's vibration, so you have more than one nucleus and they can move relative to each other. There can be rotation, since it's not a point-like particle, you can basically see the effects of rotation. And there are actually also more degrees of freedom where basically the electron spin or one of the nuclear spins or even the rotation couples within each other, so they can have all kinds of interesting coupling schemes. And this gives rise to an interesting, relatively small energy scale structure. So this kind of structure is present in nearly all molecules, and the frequencies of particularly these low frequency things are easy to synthesize, and that will play a role later on. However, what has always hindered molecular physics is that the rotational transitions and everything that's below the rotational transitions in energy, they have typical energies way below room temperature. So either you have to go very cold, or you have to live with the fact that your states are distributed over many, many states. And so typically it's very hard to look at a single molecule in a pure state. The basic problem why you can't just take our well-known and loved tricks from atomic physics and apply them to molecules is that you're very quickly lost in Hilbert space. What you would like to do is drive an electronic transition where you can exhibit the Doppler effect and laser cool, for example. But if you try to do this to a molecule, the vibration immediately gets in the way. If you do a transition to an excited electronic state, due to the finite overlap of the harmonic oscillator wave functions or nearly harmonic oscillators up here and down here, it's two different harmonic oscillators. So these wave functions are not orthogonal like you're used to from a regular normal harmonic oscillator. And you can decay to almost, well, typically at least 4 or 5 of these vibrational states. So you're immediately lost in Hilbert space. And every time you have a photon, you can also make a rotational transition, of course, because there's angular momentum. So very quickly you get lost. So there's no conservation law and there are no cycling transitions. There are a few molecules that have so-called diagonal Frank-Condon factors, and you can overcome this. And there's a lot of great research on that. But basically the message is only very special molecules can mimic the already special atoms that we can laser cool. Because when you think about the atoms, there's not the whole periodic table that we can cool either. So the ways out of this would be we just have the fact that we can only look at special atom-like molecules and that's it. Or we can build the molecules from well-controlled atoms. That's a very fruitful research that you've already seen, for example, in Kang-Ben's talk here. Or you can avoid spontaneous emission of the molecule entirely. The problem with that, of course, is that no light to observe. If there's no spontaneous emission, all the fluorescence and the usual tricks of spectroscopy don't work anymore. So what to do? I already said quantum logic spectroscopy may be the trick here. And this is why I want to introduce it a little more precisely than my hand-waving explanation in the beginning. Basically, what we do is we take a quantum logic ion that we know very well and love, and we put it into the same harmonic potential well as our molecular ion. Because they're both charged particles, they repel each other very strongly, so when one moves, the other one moves, and we have normal modes. These normal modes basically mean that we can use them as a quantum degree of freedom. And so if we select one of these shared modes and cool them to the ground state, then we can also cool the molecular ion on the same mode into the ground state. So we basically start from a situation like this. We are in the ground state as far as the motion is concerned. And the logic ion, we know quite well in which state we are. We can do optical pumping and all the usual tricks. For the molecular ion, we don't really know where we are. But let's assume it's in this state here. So now we can basically apply a blue sideband in the parlance of ion trapping to this molecular ion. We drive a transition, but in addition to the energy that we need to make the internal transition of the molecular ion, we add a little more and we also excite the motion. And the really important thing here is that if this transition actually works, the logic ion also gets excited to n = 1, because don't forget this motion is shared. So both of them make this transition, and the normal mode is in n equals 1. And that basically means that I can now shine a so-called red sideband on my logic ion here. This is a photon that would not be enough to go to the excited state if you're in n equals 0, but in n equals 1, you can go to the excited state, like so. And so the logic ion has made a transition. And if I, for example, try to drive some fluorescence from the ground state here, it's not going to work because I'm up here. And just to make sure that you can follow, if we did the same thing off resonance, so that's shown in this panel here, what happens is this first photon doesn't really work. Nothing happens. The molecular ion stays in its original state. And of course, the motion also stays in n equals 0. And now the red sideband just doesn't have enough energy to go up here, while again, for comparison, it went up to this state for that same red sideband in the case you're on resonance. And now the logic ion can actually fluoresce its state in the ground state, while up here it cannot do that. So in effect, what happens is that the logic ion state switches if and only if the molecular ion switches. And that synchronous switch can be detected on the logic ion by doing the usual tricks from our quantum logic. And therefore, that's maybe one of the most important things to take home here is the molecular ion is projected into a pure final state because this ion has made a transition and we haven't done anything to it that would change its states after that. So basically we have projected it. So I think this is a good place to, oh, there's one more thing I should say, right. For the molecules, of course, I already said we cannot use transitions that excite to the electronic excited state. But fortunately, there's another tool that quantum logic has brought about, and that is stimulated Raman-transitions. This is what we use for hyperfine ground state qubits in our research. The basic idea is that you use 2 laser fields instead of 1, and you set the difference frequency so you can make a transition in the molecule, let's say. However, you never go to an electronic excited state by just detuning this laser very far. So you have a very, very small population in the excited state, and you can basically neglect any kind of excitation in this case, but you can still make transitions here. So with these stimulated Raman transitions, you can avoid populating excited states, and all you have to make sure is that the energy difference of them corresponds to a transition in the molecule. And in this way, we can basically do research on a molecule without ever exciting it and having the decay where we lose ourselves in Hilbert space. And this is actually the place, I think, where I should take the first round of questions.
Okay, so we have already 2 questions by Bill Phillips. Let me start with the first one. It's actually a set of questions. You mentioned molecules with good Frank-Condon factors which are special. Is quantum logic a possible route to doing laser cooling on more general molecules? Not by sympathetic cooling via collisions, but in this more sophisticated way? Does this make any sense?
So I would say, first of all, hello, Bill. Good to see you or hear your question here. I can't see you, of course, but it's good that you're around and curious. I think the question makes sense. Of course, for molecular ions, we have this great tool of sympathetic cooling. And basically, as long as the masses between your logic ion and your molecular ion are not too different, this cooling can be very efficient. So I wouldn't use it in any general case. I think in the long run, we can do transitions like cooling transitions in the molecule as well. And maybe we will be lost in Hilbert space for a while after that, but we can hopefully regain our control because the molecule will thermalize and it will come back to a smaller number of states, as I'll explain later on. I think we could, of course, try out to cool the molecule directly. And in some cases, that might be an interesting thing to do. So I have to think about this a little more. As always, your questions are thought-provoking.
Okay, so then next question. When you say the motion is shared between the two ions, I assume that means there is entanglement between the two and the system is in a superposition of having the motional excitation on one and the other. What is the significance of this?
So basically, the motional mode is a mode that's just shared. It's a phonon, or as we call it. And there can be entanglement. For example, if you would make that first transition not completely, you would do something we call a pi/2 pulse, where you have a superposition of states, say. And then, of course, you would be in a superposition of moving and not moving. And only when you measure, for example, you use the readout on your logic ion, only when you measure, the system has to decide and either decide it has made this transition or not. We can use the entanglement that exists in that system, so that's totally correct. And we can actually use that to entangle the logic ion with the molecule. And I'll talk about that at the very end of the talk if I have enough time to go there. So we'll hear a little more about that.
Okay, and one more question at this point. What are the conditions on the molecular transition for the logic spectroscopy to work? Does this work for any ion?
Oh, I'm sure you'll find some exception, but what I can say is it works for most of them. And the basic condition is that you can use these far-off-resonant Raman-transitions. This will also become more clear later on. But the basic idea is that since you're using these Raman-transitions, this laser here can be very unspecific because you're not trying to look at anything particular on the molecule. So what I want to say is it works almost all of the time, but potentially not always. For example, if you happen to be unlucky and your molecule does have a resonant transition where your laser is, then of course you're in trouble, but maybe you can use a different laser then. So should I continue or? Okay, I will continue. So we wanted to try these ideas, and one obvious thing that a lot of ion trappers have struggled with is that when you have an ion in an excited electronic state, it can actually react with the background gas of your apparatus, and usually that's a nuisance. But in our case, we now deliberately do this. We basically put hydrogen gas into our apparatus, and at some point, when the calcium is in an excited state from the cooling laser, it will react with the hydrogen background gas and form a calcium hydride ion. So we load two calcium ions, and one of them, we don't know which at that time, will become the logic ion, and the other one will become our molecule. And then when this reaction has happened, the molecule decays very quickly to its electronic ground state and also the vibrational ground state, because the energies of excited vibrational states are way above room temperature. This takes on the order of a few milliseconds. But we still have all the rotational sublevels, and we don't really know exactly where we are. Just for scale, this is roughly what our calcium hydride looks like. And so these rotational states are on spacing 1 and 3, for example. That's 47 inverse centimeters, while this is 10,000 inverse centimeters. So we're really working all the way down here. I also want to introduce the molecule a little more here and explain a few things that are maybe not so obvious if you're not used to molecules. Basically, the calcium ion has closed shells and one valence electron. That's why it's nice to work with. We only have to worry about one electron when we do laser cooling and things like that. And the hydrogen also has one valence electron. It's sort of the paradigmatic one electron system, as we know. To be more noble, it would need a second electron, and the calcium it would be closed shell without that electron. So basically what the electron does when they bind together is it cheats over a little more to the hydrogen. And what that means is that basically the calcium that's already positively charged becomes a little more positively charged because some of the electronic charge that used to live over here is now closer to the hydrogen. This is a system with net charge and has no radial symmetry, so the center of mass is not the center of charge. When you talk about a dipole moment of a charged system, people get confused, but what you should do is just think about what happens when you apply an electric field. How will the system be torqued? For our case here, as I said, there's something to the left of the center of mass that's a little more positive, and then there's a little more negative way over to the right. And therefore, you will get a torque that goes this way. So the dipole moment of the whole system, the reaction to the torque, it's basically a vector that points from the hydrogen to the calcium, or if you want to attach it to the center of mass, it would point over here. So that's basically how the dipole moment works. There's one more consequence of having the center of mass and the center of charge not being the same. When the molecule rotates, so if you're in a state of rotation, basically you have this negative charge out here. It has a pretty long lever arm, about 40-1, and you have a little bit of positive charge over here. Because of the long lever arm, this charge dominates, and so there's a net charge of basically a negative fraction of an electron going around the calcium, which is like the sun here. It really determines where the center of mass is, and it's quite close to the calcium nucleus. This rotating charge creates a net negative current, and therefore you get a magnetic moment. We call it the rotational magnetic moment that points in the opposite direction of the rotation. So that's another thing you only get in a molecule, and it will play a role in a moment here. Basically, if you now look at the rotational and nuclear structure, so the part that's in thermal equilibrium, you have a lot of states. You could be in up to J equals 11. I'm only showing things up to J equals 3. And basically all these states here can be equally populated. Of course, the hydrogen has a spin 1/2, nuclear spin, and therefore there's also degeneracy. In the absence of external fields, the rotational magnetic moment and this magnetic moment would just couple together, and you get things analogous to F states in atoms. So these spins are coupled together, and you get an MF of the coupled spin. And now you can order it by J, for example, but there are always two I's. So all these states are populated, and it means that very small population is in each of these sublevels at room temperature. So what to do? There's one more complication, or actually it's an advantage in the end, that I have to introduce here. The rotation of the molecule and its rotational magnetic moment, it not only couples to the nuclear spin, it also couples to external magnetic fields. And if you look at this Hamiltonian, it looks like a bright Rabi Hamiltonian that we also know from atomic physics. It basically describes a competition of whether the spins want to follow the external field or they want to couple to each other. And fortunately or unfortunately, for a small magnetic field on the order of 0.36 millitesla, 3.6 Gauss, all these terms are about the same size. So we are neither in the Seemann regime nor in the Paschen-Bach regime. And energy levels look pretty irregular. However, there's one good thing about this, and that is we have a certain transition here, this transition, that is quite a bit different from all the other ones, and we call that our signature transition. For J equals 1, which I show here, that's 10 kilohertz. And you can look at the same transition for J equals 2, and it's 14 kilohertz, and it's also quite distinct. And it turns out for up to J equals 6, these signature transitions are all different. They actually also would be different for higher levels, but we typically don't look at them. So basically what we try to do is drive these signature transitions and see whether we can catch the molecule somewhere there. And also I should point out that these transitions, as you can see here, 14 kilohertz and 10 kilohertz before, it's only a few 10 kilohertz. They go up in frequency as you go up in J, but it's only a few 10 kilohertz. And that means your Raman system to drive these transitions can be rather simple. We used to use a 1051 nanometer laser, but that laser died at some point, and now we are actually using a different laser at about 1060 nanometers. And changing those was a matter of days. It wasn't a problem. The reason for that is that we don't rely on the resonance of this laser. We just rely on the difference frequency. And for our system, we just use two acousto-optic modulators. One is driven at some frequency nu, and the other is driven at nu plus, if we want to drive a sideband, the motional mode frequency plus whatever transition we would like to drive in the molecule. And so in our case, we are in this funny situation where the molecular transition is a few kilohertz, while our motion is 5 megahertz. So the sidebands are actually the main energy in this difference frequency. So we turn on our Raman beams here, and if we happen to hit a transition, we also have angular momentum selection rules. Sigma and pi beams give you a certain angular selection rule, where in our case you do a delta m equals +1, and then delta n would also be equals +1, a blue sideband. And if that transition happens, basically the molecular orientation changes a little bit, and they also both start to oscillate. And now I can detect this on the, I can detect this on this ion here, my quantum logic ion. What happens is we just go through these transitions and we try one of them after the other of them. And let's say we happen to be resonant with this transition here, and we don't really know in which state the molecule is. But if it were in this state, we would actually drive this transition. And that would mean if I now do quantum logic on the calcium and I ask the calcium, are you in your motional ground state or are you excited together with the molecule? The calcium would answer, I'm excited. And boom, what happens is you've projected into that state. So as soon as you get such a positive answer, you are in a known and pure quantum state of the molecule. And we can also just cool the ion back to the ground state instead of detecting. And that also creates a one-way system. And so we can basically do optical pumping. We don't have to always look what the outcome is. The environment knows anyways. And as long as we cool and provide entropy, we can prepare in pure states. So this is another good place, I think, to ask questions if something hasn't been clear.
Thanks, Didi. Yes, there have been 2 more questions already. One more by Bill. How does the calcium hydride plus equilibrate its vibrational motion? Long-range collisions with the other calcium plus would seem, and I guess I am wrong, ineffective in damping vibrational motion. How is it different for rotational motion?
So all of them equilibrate with, there is spontaneous emission, of course. Vibrational states have finite lifetimes, so they just decay even if there's vacuum around them. It's exactly the same as for atoms if you're in an excited electronic state. And the equilibration of the vibration, because vibrational levels are have big energy spacings compared to room temperature, it means you go to the ground state, just like you would go to the electronic ground state of an atom. For the rotation, you're equilibrating with the black body radiation in your apparatus. So for our case at room temperature, this means about 12 to 13 rotational levels are occupied if we just wait for the black body radiation to equilibrate. And that goes fairly quickly. So what was the second part of the question? Sorry.
The second question I haven't posed yet.
Oh no, the second part. I think there was a second part to Bill's question.
So,
or maybe I answered it already.
I think you answered it already because he was speculating whether long-range collisions won't do the job in damping vibrations, and what's the difference between vibrations and rotations.
Right. So the difference is their energy mostly, and at least for a molecule that has a dipole moment, you can always rely on this radiation coming off. If you have symmetric molecules like H2 or N2 or things like that, or N2 plus, H2 plus, you would basically remain in that vibrational state for a very, very long time. Nobody knows how long. So it wouldn't come off this energy.
And we have one more question that may not be well posed. Does the idea of quantum logic spectroscopy transfer over from the ion case to the general case of two-level systems or spins coupled to the same harmonic oscillator? How about two atoms in a cavity, for example?
I would say in general, yes. It might be really hard to implement it, but in general, as long as you have a bus, let's call it, so you could also probably do it with Rydberg states, say in neutral atoms. I'm not an expert on that, but I think in principle, as long as you have a way to do something that looks like a 2-qubit gate, you can do this to whatever system you're thinking about.
What about
I will
motional
not try to implement all of these. It could be really, really hard, but the answer is in principle, yes.
But what about specifically motional excitations in a large molecule?
I'm not sure what motional excitations in a large molecule means. You have to think about the center of mass motion and the internal like rotation and vibration of the molecule. So which part?
My guess is that it's referring to vibrations.
Okay. So as long as you can drive the vibrational transitions with, say, Raman interactions, and you can have effects on the translational motion, and you can detect that translational motion in some way, you can do this. So it really depends on the special case. I can't make a general statement.
Okay, that's it for now.
All right.
Come back later.
Sure. Thank you for the questions. So now I can start to actually talk about experimental results. So basically, hopefully it became clear that by using these tricks of projecting into a pure state, we can basically sift through Hilbert space and find where our molecule is, and by the magic of quantum mechanics, we can project into that state, and hopefully it's a pure state, but we have to show that. And one particular example, so we can do this in fact on many J transitions. One particular example I want to show here is when we prepare in a special state. And for example, this could be the m-5 state in J equals 2, or a similar state in J equals 1. And so now you're in a pure state of your molecule, and you would like to drive a transition. What we can do now is we can actually use even a carrier pulse. So sometimes I get the question, okay, there's the motion involved. Doesn't that mean if the motional energy changes, you get a problem with doing spectroscopy? But you can actually do a carrier now because you know in which state you are and you can look at departure. And the way this would work is you would drive a pipe pulse and maybe it's off resonance. So that would correspond to a place over here in the spectrum. So if it's off resonant, this transition doesn't happen and you're still in the same state. And now you can drive a sideband. And that should of course work now. It's resonant. And so you go up here. If you now ask, am I still in this state? The answer will be yes. Or have I still been in this state? The answer will be yes, because I can drive this blue sideband transition. So ask the calcium, and it says I'm in 1, so you haven't driven the transition. We are up here. If I go through the same logic on resonance, this first pipe pulse, so that would happen here when you're on resonance, this first pipe pulse can actually drive a transition. So you're going to this excited state. And if I now apply the blue sideband, that's always the sneaky trick of quantum logic. This blue sideband has a too large energy. So you're not in the right place to drive a blue sideband if you're up here. It just does not go anywhere. And so if I now ask my calcium, have I driven this blue sideband transition? The answer will be 0 or no. And in this way, I can find the probability of driving a carrier transition, which means the precision of my spectroscopy is not affected by the sideband. So the motional degree of freedom, I can basically drive the system like I would drive a normal spectroscopy system and still get a quantum logic answer. And this is basically shown for two different J states here, J equals 2 and J equals 1. We can basically go over these transitions within their M levels. And in a particular case for each of them that you can see here, you can see you get a nice line shape, your off resonance, your on resonant, and it really looks like you're talking to a 2-level system, despite the fact the molecule has a lot more levels, of course, but you've prepared a pure state and now you still know where you are. This has fairly high contrast, and so we were interested in, can we also drive Rabi flops, which are kind of the hallmark of 2-level systems? And the answer is yes, we can. Now we use different pulse times. So the length of how long we couple these systems to these levels to each other changes on this axis here. And just note that we start with a finite pulse time. That's why it's not starting up at 1, but at a finite pulse time. And we can drive a nice Rabi flop here for J equals 1 and J equals 2 again. It's not perfect contrast, but don't forget this is a molecule. So at least we were pretty proud to see this. And it almost looks like a nice qubit already. We can also do the next thing that everyone does. If you do spectroscopy, at least maybe not everyone, but a lot of people, you use pi/2 pulses. So what we do now is we drive a pi/2 pulse, then we wait some time, and then we drive another pi/2 pulse. If these two pulses are exactly on resonance, basically they just stack up and you would go to the excited state. But we can also change the phase of the second pi/2 pulse. And so depending on what we do there, after being in a superposition, we can go back down here, or we can actually go up here when we are in phase. And this is shown here for a 15 millisecond delay. So that's a fairly long delay already. It would correspond to about 66 Hertz resolution for spectroscopy. And you can see we have pretty good contrast on these Ramsey fringes. So these molecules are really nice, coherent quantum systems. Once you know how to find a pure state, you're already in business. There's one interesting side effect to this. Basically, by looking at the spin rotational structure, for example, you get a very fine fingerprint of molecules. And this is a very general concept. It doesn't only work for calcium hydride because we use very general techniques here. It's just a Raman laser. And for us, it's really just a fiber laser that we happen to have on the shelf. So nothing special about it. These couplings from nucleus to nucleus are on the range of 1 to 100 kilohertz. And the rotational magnetic moment to the nucleus is also in this range. And when we discussed with Heather what would be interesting to a quantum chemist, she basically said, oh, we would really like to distinguish isomers if we have a very small sample. For example, Heather has an ion experiment herself, and she's getting fairly small numbers of reactants. And so she would like to distinguish the isomers. This spin rotational structure here gives a very fine fingerprint. And I've just one example here where it's very obvious how it works, but you can probably imagine that even if you have a lot of nuclei and a complicated structure, when they rearrange, things will change how they couple to each other. It's a bit like chemical shifts in NMR. So this example is C2N+, and we haven't done experiments on this, don't get me wrong, but we would like to do experiments because it's a very interesting molecule. It's predicted to be one of the most abundant molecular ions in the interstellar medium. And basically, it can arrange in two ways, as you can imagine. The two carbons can be next to each other, and the nitrogen hang out, or the nitrogen can go to the middle and form a nice symmetric molecule. In one case, you have a big dipole moment, 3 Daltons, 3 dBi, 3 dBi, and it's the electronic state is a ground state, and finally, the nitrogen has a nuclear spin of 1. So it would have a fairly typical fingerprint for these spin rotational things. The CNC, the symmetric one, doesn't have a dipole moment. There's just by symmetry, it can't have a dipole moment. And so it would only have the nuclear spin. And so these two would be very easy to distinguish just by looking at the kind of spectroscopy I already showed you. And apparently this molecule is one of the most abundant molecular ions in the interstellar mediums, or so they say. But there's very little experimental data on it, so we don't really know. It would be quite interesting to look at that. And as I said, this is a general technique, so it should work for other fingerprints as well. Of course, we got a little more ambitious now. We want to also look at states where the J of the rotation changes. And for that, you need to have larger Raman splittings, not just kilohertz. We still want a universal tool. And so the trick that we want to play here is to use another technology that has made great strides in the last 20 years, frequency comps. For Raman transitions, they are particularly suitable. Imagine you have two frequency combs and they could essentially be almost in the same place. They're just shifted a little bit by AOMs again, these AOMs here. So you split the frequency comb that you have into two parts and then you run them through AOMs. If, for example, this tooth and this tooth together can drive a Raman transition in your molecule, the next one over can also do this. So they have the same spacing, so this can do it. And I can go through the whole row here, and basically I'm only running out of steam when this end of my difference frequency reaches the end of the comb. So as long as the comb is wide enough to, for example, span the population in a thermal equilibrium molecule, I should be able to drive all these transitions with my frequency comb. And so we wanted to try this out. Basically, you have to be a little more careful. You have to make sure that all these pulses, comb teeth are actually in phase with each other. So basically, we have to pre-chirp the pulse to make up for all the glass we go through until we finally reach the molecule. And we have to make sure that the pulses from this beam and the pulse from this beam actually collide on the molecule. That's what this delay is for. But once you do this, you should be able to drive transitions where the rotational state changes. And the scale for that, at least for a hydride, where the rotational structure is rather large, it's just this single proton going around its sun, the calcium, so very large rotational spacing. This is in the range of terahertz. So we were able to do this. We do the same state preparation using the CW laser as I've already shown, but now we apply a comb pulse to the molecule. And one thing I forgot to say, I should go back here, is basically you're compressing the whole rotational spectrum into one free spectral range, because any pair of these comb teeth can be in resonance if you change FAOM here in such a way that you span this one free spectral range. So you only have to look at a fairly small range. And of course, if there are a lot of lines, it could be very crowded. So that's the down part. But the up part is you basically look through one free spectral range and you're done. So we did that and we found several transitions for different J's. One more wrinkle is, since we have a linear molecule, the selection rules is we can only drive delta J equals 2. So either you absorb both rotational angular momentum quanta from both photons, or you absorb none. You cannot just absorb one because this is 2-photon spectroscopy. So delta J equals 2 is the rule here if we want to change J. And that means when we depart from J equals 2, for example, when we go in resonance here, we should also see the population appear in J equals 4, and that's indeed the case. And this also gives us confidence that we've identified these levels correctly. Otherwise, they would probably not show up in the way we think. So basically, the transition frequency for the J equals 2 to J equals 4 that's shown here is about 2 terahertz. And because we're using frequency combs and we're at NIST, we can do this with very high precision. We can basically specify this frequency here to plus minus 20 hertz. And you can also see that this is essentially a transform limited line. The line center uncertainty is on the order of 20 hertz, and you can read all the details here. But what has happened lately in the lab and gave us very great satisfaction is we were able to even improve on this. So if you look at the scale here, it's kilohertz, and the scale here is actually hertz. So James was able to improve the comp coherence quite a bit. And now we can do this with 128 milliseconds probe time, and we get lines that are just a few hertz wide. So this line is 8 hertz wide, roughly. I think this is a typo, so sorry for that. It's about 8 hertz. And we can look at the line center, and we can roughly determine it to half a hertz. That's a resolution of about 2.5 times 10 to the minus 13. You may realize that this line is at 0.6 while it was quite a bit higher up here. The reason for that is that we start to get bothered, we think so at least, by the finite lifetime in the blackbody radiation. So the J equals 2 lifetime is already such that we get some of the state depleted while we do the spectroscopy, and that's why it's probably why it's not that high. We'll find out about that later on, hopefully. Anyway, in this way, we can look at different rotational transitions and determine their frequencies with quite high accuracy. And that allows us to give rotational constants to and compare it to theory. And it's really interesting when it comes to the fundamental one, the rotational constant and the centrifugal correction, we can actually do better than theory. But then for the higher orders, the game kind of turns around here, and theory can do better than experiment. So basically the theorists are challenged here and we are challenged here, and we will keep playing this game, hopefully. Finally, one interesting thing that came about lately is we can also measure dipole moments, and that is actually a bit surprising for an ion. For example, this is the only paper I could find measuring the dipole moment of a charged ion. And basically the reason is because charged molecules are accelerated in an electric field, observation of the Stark effect becomes impractical. So you cannot apply an electric field and look at the change, or so they say. And they found a way around this. In this paper, they measured the argon hydride plus dipole moment by essentially backing it out of the rotational magnetic moments. And so the measurement wasn't super precise, but it worked. If you give this a second thought, actually, the way we trap in ion traps is by electric fields. And there is a thing called micromotion that's usually an annoyance in an ion trap, but we can actually use it to our advantage. Usually the ions want to be at the zero of the RF field, but we can apply an electric field and push them out of the zero. So this is, so to speak, micromotion anti-compensation. And now the ion is wiggling around in the quadrupole field, the micromotion. Why is it wiggling? It experiences an electric field. The field is sinusoidal, and that's why it doesn't fly away. It still stays there, but it does experience an electric field. And that means we can look at Stark effects in our ion trap. Basically, a linear molecule has a quadratic Stark effect. So even if this is a sinusoidal field that the molecule experiences, because it gets squared in the effect here, you get an average value that's not zero for the squared field. So we can actually see these. And the way we do this now is the following. We need to know what the electric field is very precisely. We can again use our tried and true calcium ion to find out what the electric field in this uncompensated place is. We put the calcium ion in this place and then look at the micromotion sideband to carry a Rabi frequency ratio. This is just a nice way of measuring the electric field, RF electric field, and it's used all the time in clocks. Then we exchange the position of the calcium and the calcium hydride. So the calcium hydride sits in the same field as the calcium was sitting before. And now we measure a rotational transition of the calcium hydride and basically look at how the frequency changes as we change the electric field. This works really nicely when we plot the square of the electric field versus the change in the frequency. We get a fairly nice straight line, and in fact, by looking at the slope of this line, we can find the dipole moment of our calcium hydride molecule. And we can find it to a fairly good precision, certainly better than the precision for the argon hydride plus case. It's not quite as good as for neutral molecules yet, but this is the first time we've tried this, so maybe we can clean up our act. I think I'm getting close to running out of time, so I'll not go through the details here. I'll just tell you that we were able to entangle calcium and calcium hydride essentially just by doing a pi-halves pulse rather than a pi pulse to the molecule, and then not doing the quantum logic, but just leaving the calcium alone after we've done the red and blue sideband. And so basically what we're doing here is we have the calcium in an S or an excited D state, and at the same time the rotation is in two different levels. Rotation is sort of a Hilbert space that has no bounds, and you can go to higher and higher excited states. So basically you can think of that as a rotational cat state here. So in the cat analogy, this would be the atom and this would be the cat. So this is a really small kitten, but it was great fun to produce this, and entangled state fidelity was about 0.87. So it's not perfect, but hey, these molecules are pretty good qubits. And with that, I'm at the summary. I hopefully convinced you that quantum logic provides a general method to enable coherent manipulation of charged particles, and in our particular case, molecules. And we can prepare and manipulate the quantum states of the rotation and detect their changes for a single molecular ion with high fidelity. Thinking about what we could go from here, where we could go from here, this should work for, if we think about a singly charged polyatomic molecular ion, it should work to a mass up to approximately 500 AMU. Basically, the Q over M of the molecule you want to look at has to be within a factor of 3 roughly of the Q over M of the ion you're using. So going to these high numbers of mass here, you would have to use a more hefty ion as well, for example, ytterbium. We can already control the spin rotational transitions, as I hopefully convinced you, and we can entangle the atoms and the molecule. Hopefully soon we can use a similar technique now with 2 frequency combs to do vibrational transitions. We hope to look at that in the very near future. The way I like to think about this is that we've built a special purpose quantum machine that basically runs algorithms. We have to make decisions along the way here, whether we are in a state or we haven't quite prepared it and so on. And here, rather than simulating molecules, we actually learn about the real molecules. And basically we do this 1 qubit at a time. So every time we interrogate our logic ion, we get 1 bit of information. Or if we don't inquire, we have entanglement and it's more like a qubit. So that's all I have to say for today. Of course, I always have to thank the group. I'm lucky to be the spokesperson here, but all of this happens in an environment of very talented people, and we would really be nothing without them. And the other thing I want to say in that context is, of course, this is just a small part of what we do in the ion storage group. And if you want to learn more about this, stay tuned for talks from the ion storage group here or in other places, hopefully. Thanks for your attention.
Thanks, Didi, for this really exciting talk. We have a couple of more questions. The first one from Mackenzie Zubin. For the Raman transition, is the main scattering rate due to the upper electronic state? Do you see influence from the higher vibrational states, or are the Frequenton factors too weak?
So basically, when you look at the vibrational transitions, there is a very small influence from those. So mostly our Raman transitions are driven through the excited electronic states. I wouldn't call it scattering because we are detuned by an enormous amount. So I really more like to think about it that you have your ground state molecule, it has an electronic state, and your Raman beam just deforms it a little bit. And that deformation basically drives the transition inside. So our overlap with the excited state is very, very small. But if you look at how it happens, it's mostly the dipole matrix elements with the excited states, but we are very, very far detuned. In fact, we are so far detuned that the counter-rotating term, where you basically emit a photon before you absorb it, so you're even more detuned in your intermediate state, that plays a role, and we have to account for that. So basically, it's the electronic states, but we are not really populating them at all.
Okay, Maciek, thanks you. Very impressive. And I go on with more questions from Bill. Would you say a little more about where the entropy goes when you cool something by observing what state it is in?
So that's a very interesting question that I asked myself. I think, as we all know, or most of us, I don't know, sorry. Anyway, entropy is actually an informational concept. And I think basically here we have a fairly clean example of we actually learn something about the system. And of course, as I said, you can also just cool the motion away that tells you about the system. But basically the measurement, the act of measurement, as far as I can tell, is where we have the entropy go away. And basically we pay the price by having to go and search through the Hilbert space quite a bit before we find the state for the first time. So that's sort of the price of, you have to rummage around like Maxwell's demon almost. But once you do such a projective measurement, and that's the case for any quantum system, I think, if it's a non-destructive measurement, like it is in this case, you have removed the entropy. I don't think I can say anything more profound than that, because at least everyone I know still has struggles with this concept. But in this case, we can see, hey, it works, and we can use it to our advantage. And so I'll take it.
Okay, so let's go to the next question. The upper trace for the J equals 1 Ramsey doesn't look like a good fit. What's the explanation for this?
Doesn't look like
a good fit.
Oh, okay. Oh, wow. Let me see. Here we go. So I think basically the question is about these points here. So I think the explanation is that something in the experiment drifted. One thing I swept under the rug a little bit is because this preparation is fairly inefficient right now, these experiments take a long time. So I would guess this Ramsey trace here, you also only get 1 bit per experiment. This trace probably took something on the order of at least half an hour or so. And so I think what happened here is the system drifted a little bit. So if you wish, the not so good fit is still experiment, still learning the tricks here and not being able to keep things stable as much as we would like it.
Okay, so I think we have maybe time for 2 more questions. One from Brandon Iritani, perhaps a somewhat naive question. How do you control the Raman light shifts with the comb spectroscopy?
Yeah, and again, this was something I had to sweep under the rug. Basically, we have to make sure that the rep rate of the comb is in a place where this Raman shift is relatively small. And then the other thing we do is we use fairly weak beams, actually. So I think the question is basically about the AC Stark shift and the 4th order shift from the comb. So the 4th order shift we can avoid by going to the right free spectral range of the comb, where we largely avoid this. And then by just turning down the intensity, you can reduce the AC Stark shift. And typically we do the measurements in such a way that we try at different intensities of the comb and then extrapolate to 0 intensity. So this has to be taken into account if you do precision spectroscopy.
Okay, let me ask you one more question that I myself find also interesting. It's by Philip Schindler. If you have a more complex molecule, you need to include more rotational states. It might be populated initially. Can you estimate how many levels can be populated before imperfections in the readout become a problem?
That's a very good question, and I think I don't have a perfect answer for it. What we want to do is, this was all at room temperature because it was convenient. If you go to more complex molecules, your 1.1% population goes down in a hurry. And we all know that Hilbert spaces tend to explode. The one thing we can do is we can actually go to a cryogenic environment, and we will actually go to 4 Kelvin. So that will hopefully make things better. But it's pretty clear that if you have a more complex or complex enough molecule, it will be very hard to find the signature transitions that we're using right now. And basically, my best answer here is we have to learn to walk before we run. And at some point, this will be a limitation. So I'm not expecting to look at some really complex protein and know every vibration and every rotation of that big old molecule. But who knows, maybe people are smart and find ways to do this. Are there any more questions or?
I think we're out of time, so there are a couple more, but we'll send them to you in writing.
Yeah, I'm happy
and over
to
to
answer them.
Sebastian now for the conclusions.
All right. Thanks
All right.
everybody for coming, and it was great fun to be here.
Yeah, thank you very much, Didi, for a very cool talk. Lots of new things in there. And like to also highlight again that next week on April 22nd, we will have our third Hot Topics session, where we'll have 3 talks by Maja Kolawiti, Tom Dara, and Daniel Gonçalves Romeo. And you should certainly also check out our sister seminar, the virtual AMO seminar, where tomorrow they will have Gerhard Rempe speaking about quantum networks. If you want to get notified about what we do, please go to our website, quantumscienceseminar.com. You should subscribe to our email list and to our Google Calendar, and you could even follow us on Twitter. With that, I'd like to thank you for your interest, and we hope to see you again next week. Same time, same place. Bye.